Hey everyone, welcome to our next section on chemical reactions. We're going to go through just kind of some basic stuff on balancing equations and taking a look at different reaction types and into some solubility stuff. And so hopefully the examples will make a little bit of sense as we go through, and you can certainly ask questions if you get stuck. So when writing word equations out, we can kind of get an idea on how reactants can make products. And so we have this arrow that's kind of leading from one side to the other side. We have iron added to oxygen, which gives us iron 3 oxide. Note that there's a plus sign in there which separates the chemical formula, and that would happen on either side of the reaction. In this case, the product side doesn't have an extra chemical formula. There's only one, so there's no need for that plus sign that's there. But basically things that separate compounds are plus signs and arrows. So you'll only see one arrow in a reaction, typically going from reactants to products, and there can be many plus signs in there depending on how many chemicals are being added together, or separated, I guess. So, a chemical equation, I'll make this a little bit bigger. A chemical equation can replace the words by their symbols instead. So I could, for instance, get rid of, instead of saying iron plus oxygen, we could have iron and oxygen gas, which gives us iron 2 oxide, or Fe2O3. This is kind of known as our skeleton equation. So a skeleton equation is a chemical equation that doesn't indicate the relative amounts of the reactants and products. And so we just have our equation kind of written out with our arrow as we can see it here. To add more information into the equation, we can introduce the physical states of substances by putting symbols after each one. So you'll often see something like an S for solid, or an L for liquid, or a G for gas, that are normally lowercase written after each element or compound in italics. And you'll also come across this one that's AQ, and AQ just stands for aqueous, and so it's for a substance that's dissolved in water. So the chemical equation that we have above, that's here, we can now kind of expand it a little bit more. We can see how it's Fe solid, so it's solid iron, oxygen gas, and it makes solid iron 2 oxide. So, in many chemical reactions, we can also have this idea of a catalyst. And so, a catalyst is added into the mixture and it speeds up the reaction process. But it's not used up, it's just there to speed up the reaction. So, where it's neither reactant nor product, it gets written above the arrow in the chemical reaction. So, in the example that I have here, we have hydrogen peroxide, H2O2, and they're using manganese oxide as the catalyst, and it's basically decomposing it into water and oxygen gas. So just as an idea to say like what it looks like when it's placed in a reaction. So a triangle or heat written above the reaction arrow indicates that heat's being supplied to the reaction. So if we were to see heat somewhere, it's basically saying that heat is being supplied in the reactants and it's causing the products to form faster. In many chemical reactions, let's go ahead, in balancing equations, when we balance a chemical equation, there's a few guidelines that can help us out along the way. I've given you guys a handout sheet, attached the link to it in the handout section. I would encourage at this point that you kind of pause the video, go to that balancing sheet and have a read through and just kind of see if you understand the different levels that are there that it talks about in terms of difficulty for some of these balancing equation questions. And if you have any questions, let me know. So pause the video, I'd go to that section now, take a look at the handout sheet, understand kind of what it is that they're saying in terms of balancing equations, and then when you come back, we're going to go through some examples. Alright, so example number 1, we've got tin 2 oxide plus hydrogen gas gives us tin and water. And so we need to balance this thing out. We need to make sure that it has the correct number of moles for each element, and they can only be added in the coefficient spot. That's really important. So I can only add things in the coefficients area. So that means that I remember plus signs and arrows we said kind of separate chemical equations. So that means that I can only really add something in the front of each compound. So in this case I have 4 spots that I can add something in. So the first thing I would do is I would list each element, S, N, O, and H. Okay, tin, oxygen, hydrogen. And then we should have the exact same thing on the other side because this thing has to obey the law of conservation of mass. So whatever elements are present in the reactants should be the elements present in the products as well. And have a little line between them. My left side's my reactants, my right side's my products, and then I'm going to start to count atoms here. So if I take a look at tin on the left-hand side, there's only 1 atom of tin present here. That's why it's not really written in the 1. Oxygen, there would be 2, and hydrogen, there would be 2. Tin on the right-hand side, there's 1. Hydrogen, there's 2, and oxygen, there's only 1. So I can see that if I look from left to right here in terms of counting my atoms out, tin balances out and hydrogen balances out, but my oxygens don't. And so because of that, I have to start to add numbers in the coefficients place that's going to help me balance this out. So I'm going to begin by balancing out one side. I can't make numbers smaller, so I can't reduce anything, and I can't insert numbers in between chemical equations. So like for instance, I couldn't make this tin 2 O2 to help balance something out. Numbers can only ever be added in the coefficients place. So if I have hydrogen that's here, I'm going to need to balance out, oxygen that's here, I'm going to need to balance out my oxygen to make it so I have 2. And the only way I can do that is through multiplication. So 1 times something gives me 2. And if I see, hopefully I can put a 2 in this spot. So what happens is 2 multiplies the 1 oxygen that's there, and it gives me 2 oxygens now. Now, it also changed the hydrogen count. 2 times 2 gave me 4. So that changed my overall part, but if I look now, tin still has 1 atom in each one. Oxygen now has 2, which is the reason for doing that step. But now I have a problem with my hydrogen that it's not balanced anymore. And so if I look at my equation of my reactants place, I realize I can put a 2 in front of the hydrogen gas that's there. 2 times 2 gives me the 4, and now I have a balanced chemical equation. It has the correct number of atoms on the left-hand side as it does on the right-hand side. So at the end of it, I always write out my coefficients. Whatever place has a blank is a 1. So I open up a square bracket, and this is 1, 2, 1, 2. Okay, the numbers written out in my coefficients place, and it's balanced and completed. So for example 2, we're going to run through the same steps again just to kind of give you some examples here on how they go. So these are those level 1 kind of questions from the handout sheet where it just gets you to kind of go through a straight balancing process. So I've got carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen, and I'm going to look to balance these out. So carbon on the left has 2 atoms, hydrogen has 6, oxygen has 2. Carbon on the right side has 1 atom, hydrogen has 2, and oxygen in this case actually has 2 from one and 1 from another one. It has 3 in total. So when this happens, and these kind of questions do arise quite a bit, I tend to save that oxygen for the last, because it's really hard to try to figure out how to balance it when you have 2 on one side, because as soon as you change one thing, it kind of changes your oxygen count and affects 2 terms. So I'm going to start with my carbons and just work my way left to right and move to hydrogen and then see how my oxygens look after that. So my carbon count right now has 2 on the left, 1 on the right, and I know I can only put numbers in the coefficients place. So that means that if I put a 2 on my right hand side, that gives me 2 carbons, but it also changes my oxygen count to 4 on the first term plus the 1 more in the second term, so it actually changes it to a 5. Now, my carbon's balanced, but I have to take a look at hydrogen now. Hydrogen looks like it's going to need a 3 in that coefficient's place, and that gives me 6 hydrogens on the right-hand side to balance the left-hand side, but again, change my oxygen count to 4 plus 3 more now gives me 7. So now, my carbons and my hydrogens both balance. Now if I look on the left-hand side, I have a smaller value there. I only have 2 atoms of oxygen. And on the right-hand side, I have 7. There's a little bit of a trick with this where I'm going to write out what it would take to balance this, and then we'll kind of see how we can manipulate that formula. So 2 on the left-hand side, if I had a 3.5 here, 2 times 3.5 gives me 7. But I can't have decimals as moles. I can't have a 0.5 as a mole value. These numbers have to be whole number values when we start to work with them. So I know that this actually works because now I have 7. And so what I actually need to do, or the trick that I can use to get around this, is now to go through and double everything. So what was a 1 in front of C2H6 now becomes a 2. The 3.5 now becomes a 7. The 2 now becomes a 4. And the 3 now becomes a 6. And if I take a look and start to count my atoms here, I've got 4 carbons on the left. I've got 4 carbons on the right. I've got 12 hydrogens on the left, and we have 12 hydrogens on the right. And I have 14 oxygens on the left, and 14 oxygens. 4 times 2 gives me 8, plus 6 more, 14 oxygens on the right. So by doubling everything, I'm getting into whole numbers, which is allowing me to get to my answer with the coefficient values of 2, 7, 4, and 6. Okay, so hopefully you're kind of getting the idea on how to go through these. In example 3, this one, if we look at our handout sheet and our levels, this one has common polyatomic ions that show up. Do you see how these NO3s show up in both? And these OHs show up in both? Because of that, I can actually treat them as a term, treat them as one thing. I don't need to separate them into oxygen and hydrogen and nitrogen. So I'm going to start off and write my calcium, and then I've got NO3, and then I have a K, and then an OH. And the same thing on the other side. Calcium, NO3, K, and OH. I'm going to encourage you to pause the video here and just try this out. See if you can get it to balance, and come back when you're ready to go over the answer. Alright, so on the left-hand side, calcium has 1 atom. NO3 in this case, there's 2 of them because of the 2 that's here. Potassium only has 1, and hydroxide has 1. Calcium on the right-hand side, there's only 1. NO3, there's only 1 of those, 1 nitrate. There's 1 potassium, and there are 2 molecules of hydroxide there. So now I can see it's not balanced out right away, so I'm going to have to try to go through my steps. I'm going to start with calcium. It's balanced. I don't need to do anything there. NO3, there's 2 on the left and 1 on the right, which means I'm going to place a 2 in the front. Remember, I can't place anything in between values, so I can't like put a bracket around NO3 and add a 2 in. I'm only allowed to put things in the coefficients places, which are at the beginning of each compound, separated by plus signs and arrows. So now that I put a 2 in front of the NO3, that makes this a 2, but it also changed my potassium to a 2. So that's okay, I can go over here and add in a 2, which changes my potassium to a 2, but it also changed my OH to a 2. And now when I look at everything, I've got 1 calcium on each side, 2 nitrates on each side, 2 potassiums on each side, and 2 hydroxides on each side. It's balanced. And so my final value for this, filling in the 1s in those blank spaces, is 1, 2, 1, 2. So kind of moving into some of the different levels here, this one is a word problem one. And so this actually asks us to make the equation, then balance it, and then there's a question at the end just saying what kind of reaction is this. So let's kind of take a look here and see if we can't make the equation from this. Carbon dioxide, okay, carbon dioxide is CO2. We're going to add to that some water, some carbon dioxide and water. reacts with sunlight, so sunlight is kind of our catalyst in this whole thing, to give glucose, which is sugar, and I don't expect you to know right off the chemical formula for sugar, but you can certainly look it up, and it is C6H12O6. And it also gives off some oxygen gas, okay, O2. If I want to add in my state changes here, carbon dioxide's a gas, water is a liquid, sugar is a solid, and oxygen gas, it's a G for a gas. Now I can only add numbers in the front here, remember, so numbers can only show up in the front place of each of them, because now I need to try to balance this. So I've got carbon, we've got hydrogen, and we've got oxygen. Okay, carbon, hydrogen, oxygen. Deal with your carbons and your hydrogens first. When these kinds of problems arise that deal with carbon, hydrogen, oxygen. Okay, deal with carbon first and then hydrogen second. So I'm going to count my atoms out. I've got 1 carbon, I've got 6 on this side, I've got 2 hydrogens, we've got 12 on the right, and in oxygen, looks like there's 3 on the left, and oxygens looks like there's 8 of them on the right. So take a second, see if you can balance this, and come back when you're ready. Alright, so my carbon on the left hand side, so I only have 1 there. This needs to be a 6 in order to balance this out to make it the same as the right hand side, which affects my oxygens because now I have 6 times 2 is 12 plus 1 more makes 13. Then I go to my hydrogens and it looks like I've got 2 on the left, 12 on the right, so I'm going to need a 6 to go in front of my water. That's going to give me 12 hydrogens, but it's also going to change my oxygen count from 13 now. 6 times 2 is 12 plus 6 more is now 18. And then now that I see my oxygens don't work, the smaller numbers in the product side, I go over to my O2. I have to think, okay, I need to make 18 oxygens here. Well, there's already 6 taken up there, so really I just need 12 for the remaining little bit right here. So that means I need to put a 6 here. If I put a 6 there, 6 times 2 is 12, plus 6 more gives me 18, and it looks like this whole thing is balanced out. So my coefficients at the end are going to be 6, 6, 1, 6. And what kind of reaction is this? So it's something that takes in carbon dioxide, takes in water, and it releases oxygen and sugar. Any idea what kind of reaction would take in carbon dioxide, a little bit of sunlight, water, and release oxygen? It is photosynthesis. Alright, so you've seen lots of problems. The more comfortable that you get with balancing equations, you don't necessarily have to do this whole middle step all the time. It's mostly just to get you started and especially help organize those numbers. But the more comfortable you are with them, you can certainly just jump to those coefficient parts and then just kind of write out your answer at the end in terms of what the coefficients are. So there's a couple of questions to get you started and a couple of assignments to work on the website. So let me know if you have any questions.